Imagine the universe as a giant, stretchy sheet of fabric, space-time. This fabric is everywhere, invisible yet fundamental, stretching across the cosmos and connecting everything within it. It's not just an abstract idea, it's the very stage on which all cosmic events unfold. Massive objects like stars and planets create curves in this fabric, guiding smaller objects along their paths. The more massive the object, the deeper the curve it creates. This is why planets orbit stars, and moons orbit planets. They're following the curves in space-time made by gravity. A black hole is an extreme version of this concept, where space-time is warped so intensely that nothing, not even light, can escape. The gravity is so strong that it creates a region from which no information or matter can return, making black holes some of the most mysterious objects in the universe. Think of it as a bottomless pit in the cosmic fabric, a place where the rules of physics as we know them break down. Anything that crosses the edge, called the event horizon, is lost to the outside universe forever. If our sun were replaced by a black hole of the same mass, Earth would continue its orbit, but it would be very cold. The black hole's gravity would be identical to the sun's at this distance, so our planet wouldn't get sucked in. However, without sunlight, life as we know it would quickly disappear. Black holes aren't cosmic vacuum cleaners. Their danger lies in their steep gravitational pull. Only objects that venture too close are at risk of being pulled in. From a safe distance, they're just another massive object, but up close, their gravity becomes inescapable. They form from the collapse of massive stars, whose cores shrink into an incredibly small point. When a star runs out of fuel, it can no longer support itself against gravity, and its core collapses under its own weight. This point creates an infinitely deep well in space-time, birthing a new black hole. These cosmic enigmas challenge our understanding of physics, and continue to fascinate scientists and stargazers alike as we strive to unlock their secrets. Black holes come in a surprising variety of sizes and types, each with its own unique story and place in the cosmos. These mysterious objects are not all created equal, and their differences reveal much about the universe's history and structure. The most common are stellar mass black holes, which form when massive stars reach the end of their lives and explode in spectacular supernovae. These black holes typically weigh between a few and about 100 times the mass of our sun. As the core of a dying star collapses under its own gravity, it creates a region so dense that not even light can escape. These stellar mass black holes are scattered throughout galaxies, often hidden from view unless they interact with nearby matter. At the other extreme are supermassive black holes, which lurk at the centers of most large galaxies. These cosmic giants can be millions or even billions of times more massive than our sun, and their immense gravity shapes the evolution of entire galaxies. Our own Milky Way harbors a supermassive black hole called Sagittarius A star, weighing in at about 4 million solar masses. It sits quietly at the heart of our galaxy, occasionally flaring as it consumes stray gas and dust. Between these extremes are the elusive intermediate mass black holes, with masses ranging from 100 to 100,000 times that of the Sun. Astronomers believe these may be the missing link in black hole evolution, but only a few candidates have been found so far. Some scientists think intermediate mass black holes could be the seeds from which supermassive black holes grew, merging and accreting matter over billions of years as galaxies formed and collided in the early universe. By studying each type of black hole, astronomers gain valuable insights into the universe's evolution, the life cycles of stars, and the powerful forces that shape galaxies across cosmic time. As you approach a black hole, the universe transforms before your eyes. You'd see a perfectly dark sphere, the event horizon, looming ahead, marking the ultimate boundary in space. This is the infamous point of no return, where not even light can escape the black hole's grasp. The closer you get, the more distorted the stars and galaxies around you appear, as gravity bends light in strange and beautiful ways, creating a surreal, almost hypnotic view of the cosmos. Beyond this invisible threshold, gravity becomes so overwhelmingly strong that escape is utterly impossible. Anything that crosses the event horizon, whether it's a star, a planet, or even a beam of light, is lost forever to the black hole's depths. The laws of physics, as we know them, simply can't save you here. Deep inside, at the very core, lies the singularity, a point where matter is crushed to infinite density and the fabric of space and time is warped beyond recognition. Here, our understanding of physics completely breaks down, and the rules that govern the universe no longer apply. But before you even reach the event horizon, you'd experience a bizarre phenomenon known as spaghettification. The tidal forces near a black hole are so extreme that they would stretch your body into a long, thin strand, pulling you apart atom by atom in a process both fascinating and terrifying. Surrounding many black holes are brilliant accretion disks, rings of superheated gas and dust spiraling at incredible speeds. These disks glow intensely, emitting powerful radiation as matter is torn apart and consumed by the black hole's gravity, making them some of the brightest objects in the universe. We can't see black holes directly, but we detect their presence by observing this chaotic, flickering light show. It's through these energetic emissions and the violent dance of matter around them that we uncover the secrets of these mysterious cosmic giants. Black holes sometimes find each other, engaging in a cosmic dance. As they spiral closer, they create ripples in spacetime, gravitational waves. These waves stretch and squeeze space, carrying energy and information. Detected by LIGO, these waves reveal the cataclysmic events of black hole mergers. LIGO's sensitivity is extraordinary, measuring changes smaller than a proton's width. This technology allows us to hear the universe's most dramatic events. On May 21, 2019, LIGO detected a groundbreaking gravitational wave signal. It came from the merger of two black holes, one 66 and the other 85 times the Sun's mass. This event, GW190521, confirmed the existence of intermediate mass black holes. The collision released immense energy, converting mass into gravitational waves. This discovery challenges our understanding of stellar evolution. Gravitational wave astronomy is just beginning, with future missions like LISA set to explore more cosmic mysteries.